Thank you. Okay, so we're going to go over quiz number 5. Let me go ahead and go share the screen. Okay, let me see, minimize this out the way. All right, quiz number 5. Okay, so just go through it. If you have any question, please go ahead and ask. So this is, like I said, we're going to go over quiz number 5, the transistor. That was taken on November 2nd. Okay, so number 1, common emitter transistor circuit, the AC input signal is applied between the, okay, so you're going to put inside the base here. It's going toward the base. Okay, so the base and emitter, since emitter is the common, so therefore it's going to be the base and the emitter. So the answer is D as in David for number 1. Number 2, in a CA transistor circuit, the AC output signal is taken between the mainly the collector and the ground. So it's going to be at this point and ground. So as you can see, it's got amplify, and so it's collector and ground. So the answer is B as in Bob for number 2. Okay, any question number 1 or 2? Okay, no question. All right. So question number 3, in a CE transistor circuit, what terminal is common to the input and output signal? Okay, so CE, both common, would be according to the collector, the emitter. So it's going to be right here. It's connected to the ground. So it's at the emitter, okay? So the AC voltage gain, okay, number 4, the AC voltage gain in the CE circuit is typically, it should be more than 1 because you got a small signal that is come at the input is coming through the base, and your output is collected at the collector, which is going to be amplified. Okay, so your gain is going to be greater than 1. Okay. All right, any question number 3 or 4? Okay, no question. Next. Okay, when a CE transistor circuit is used as an amplifier, okay, so for number 5, so the answer is C, the base collector junction is reverse bias. Okay, so right here, so they want common emitter. So common emitter is connected here. So from here to here would be forward bias, but from the base to the collector, it should be in reverse bias. Okay, so the answer is C on that one. Number 6, the CE transistor circuit exhibit, okay, all the above. It will provide high gain, high voltage gain, high current gain, and high power gain. So if you want to design the circuit to get all the highs, you have to use a common emitter. Okay, so the answer is D as in David for number 6. Okay, any question number 5 or 6?
Nope.
Okay. Question number, okay, let me see if I can enlarge this one a little bit bigger. Okay, number 7. Okay, number 7, at saturation point of a CE transistor circuit, the collector current is at maximum. Okay, so this is right here, it's showing at saturation. Okay, at saturation, we got the maximum amount of current possible in the transistor. Okay, so that's your IC at saturation. So your collector IC or the collector current is at maximum. So the answer is A as in apple for number 7. Number 8, the beta DC equal to, it's going to be IC over IB. So this is it. So this is a symbol for, if you look at the data sheet, it's lowercase h, and then capital FE. That represent your DC gain. Okay, it's going to be IC over IB. So the answer is B as in Bob for number 8. Okay, any question of 7 or 8? Okay, no question. Next. Okay, so number 9, the AC voltage gain of a CE transistor circuit equal to the AC collector voltage divided by the AC base voltage. Okay, So that's your gain right here. Gain equals V out over V in. Okay. So your V in is going to be going through the base, and then your V out is going to be coming collected at the collector. Okay. That was this circuit right here. So your output is at the collector, your input is at the base. That's how we got that formula. Okay, so this formula here, okay, saturation, and that's there. Okay, so number 9, okay, so that's 9, the gain. Okay, the optimum Q point is located pretty much at the center of your DC load line. Okay, so this is your DC load line, and it's right in the center. And this is your active zone from here to here. This is where most of the signal will get amplified. Okay, so therefore the answer is D, at the center of the AC load line. Okay.
Is it sorry, Sam, is it interchangeable? Because it says AC load line, and I didn't know if that was a typo or if that was a trick.
Yeah, mainly we use mainly we look at the AC. Yeah, mainly we look at the AC when we're looking at the yeah, you can interpret it AC or DC. Mainly we look at the, so all the capital letter here is represent DC DC. So the answer is D, at the center of the AC load line. Okay, so any question number 9 or 10?
On number 9, I guess maybe we're playing around with these letters, the size of the letters.
Yes.
Because it's collector number C it's got a little c and a little b.
Number C here?
Yeah.
No, that's a capital VC over VB.
So that's that. So C is for DC, then you're saying, huh?
Yeah, all capital letters.
I get what you're saying, Sam. I guess I got screwed up looking at the little letters there.
Yeah, it's mainly we're looking at the gain of the AC signal. So yes, because we use the DC is just to bias the transistor.
No,
we use the AC signal to control the current.
I guess I got tricked up on the letters, the size of the letters.
Right. Okay.
Because you can easily interpret that is because it's VC over VB.
Right, because if you look at B here, look like they're almost the same size as the letter C. So therefore that must be capital letter. And anything that deal with capital letter, that deal with DC voltage.
What current is flowing first, the AC current or the DC current? Is the DC current considered to be a conditioner for the circuit before the AC actually starts to take over?
DC mainly just to bias the transistor to make sure that the transistor work. And the AC signal would pass the AC signal in and out.
So the DC isn't necessarily a conditioner or a prep for any circuit that has to flow one direction or the other, since the AC has the ability to go from one direction forward and then backwards, and then the DC is strictly only one way.
Correct. DC is only one way. Only the AC would be flowing in reverse bias and forward bias.
Right. So C1 and what's that? C3. The current's only specifically going one way, but that's being blocked.
Yeah.
That's C1 and C3. So technically, I mean, C3, the directions for DC is going right, and then.
Yeah, so that one, the DC would be flowing through this way to bias the transistor, but it does not have to deal with anything about the output. The output is only the AC signal that would go through the capacitor.
Right. I guess what would be in consideration a confusing analyzation is, from the transistor, you have current on the left side for C1 and then current on the right for C3. So technically, they're only going straight line as far as the signal, the visual signal when you see it as a square wave versus the AC is showing the oscillation as a 360-degree circular movement. So I guess to interpret the signal on the oscilloscope, one straight line DC versus AC oscillating negative to positive, you'll never see the negative DC. I mean, you'll never see a negative DC at C3 or C1, correct?
Correct, because they only go straight line, either one way or the other. They're gonna block the DC no matter what. It block the negative as well as the positive.
Right. So the confusion would be, regardless of how that schematic says, it looks like DC is going right and DC is going left. DC doesn't have oscillation. Just
Yeah, DC would get blocked right here at the C1 as well as at C3.
right.
So that's why the DCs only go through and then just turn on the just operate turning the transistor on or off. That's it.
Right. All right. Thank you. Excuse me.
Okay.
So Sam, 9 is A and 10 is B, right?
Yes,
All right, that's all I need to know. Okay,
Okay.
thank you.
you're welcome.
Sorry, Sam, one more thing, just to understand, is the AC load line the same thing as the DC load line? Because just so I'm clear, because you said DC load line was the answer, and clearly D does not say that. I just want to understand if it's the same thing, because I thought they were different.
Yeah, they're different because mainly when we look at like we just said a minute ago, you have the DC, just the bias, the transistor, but the AC load line is the one that we have to look at because that's where the current would be flowing.
Okay, is the Q point then the center of both DC and AC load lines regardless?
Yes,
Okay, thank you.
you're welcome. Okay, so that's number 9 and that's number 10. Okay, so next set. Okay, the coupling capacitor in RC couple amplifier. We just said that a minute ago, passes AC signal, but block DC signal. That was just the 1 minute ago that we just discussed. So the answer is B as in Bob for number 11. Number 12, when a high amplitude signals is applied to the input of an amplifier that's designed to operate with low amplitude signal, the output signal is distorted. Yeah, so your signal would be chopped off. So whatever the amplifier can go up to, that's it. If it goes up to, if it's set up for 12 volt, positive 12 volt, negative 12 volt, and you put in more voltage through the input, and then when you look at the output, it would get cut off because if it get amplified to like 15 volt, but the designer of the transistor is only 12 volt, so therefore it's only displayed for 12 volt, and anything else above that it's going to cut, and the bottom is going to be gets cut off on the bottom. Okay. So the answer 12 is C. The output signal is distorted. So any question number 11 or 12? Okay, no question. Next step. Okay, 13, the term gain describes the increase in. Okay, so gain is all the above. Okay, you got the voltage gain, it's VC over VB, or current gain, it's IC over IB, or power gain, it's going to be, just applying IC times VC divided by IB times VB. Okay. So any one of them, A, B, and C is correct, but the overall, so all of them is correct. So the answer is D, as in David, for number 13. Number 14, to increase the voltage gain in a common base transistor circuit, what resistor should be increased? Okay, so we know that the gain is over VC over VE. Okay, so VC over VE. So therefore, so in this case, we're going to increase the resistance on the collector. Okay, so the answer is A for number 14.
Number 13, if we pick one of them, I mean, we correct or no?
You partially correct because the other one also correct.
Okay.
So the answer D would be the overall. So the answer A, B, and C is correct. So
Okay,
the answer D would be correct.
thank you.
You're welcome. So any question on 13 or 14?
No more.
Okay. All right, so number 15, a common base transistor circuit, the AC input signal is applied between the, okay, so you're gonna be the common base, so the base is right here, so you're gonna be, your input would go toward the emitter and base, so the you gonna be measured since the base is connected to common, that's why it's an emitter and base. Because the high side you put at the emitter, and then the common would be the low side would connect to the common or the base in this case, since the base is connected to the common. Okay, so the answer is C for number 15. Number 16 is in a common base transistor circuit, the AC output signal is taken between the mainly you're going to be coming out from the collector, so it's going collector here. And your low side will be connected to the common. Common is next to the base, so therefore it's connected, collector and base. So the answer is A as in apple for number 16. Okay, number 17. The common base transistor circuit, which terminal is common to the AC input and output signal? Okay, so common base would be right here. So therefore it's connected to the base terminal. Okay, so the answer is C as in cat for 17. Okay, any question 15, 16, or 17? Okay, next set. Okay, this would be the last. Okay, so the common base exhibit, circuit exhibit. Okay, so we're going, that is just the characteristic. That is, you can look at the handout from the website, this one from Mr. Pham. So common base, so the base is so follow this characteristic. So low current gain, so there's a no current gain, so the answer is so the CB is low current gain but high voltage gain. Okay, so no current gain but has a high voltage gain, so this one right here. Okay, common base. All right, so okay, so that's gain is going to be less than 1. Okay, so B as in Bob for number 18. Number 19, in a common base transistor circuit, which terminal is common to the AC input and output signal? We just talked about that. That was the base. Okay, so the answer is C, the base terminal. Okay, number 20, the point on the load line where the DC operating collector's current of the transistor circuit and this DC operating VBE intersect is the Q point. Okay, so yeah, here they're talking about the load line DC operating, so Q point is right here, right in the center. Okay, so the answer is B as in Bob for number 20. So any question number 18, 19, or 20?
No, thank you.
Okay, everybody's good. Thank you. Okay, back to you, Mr. Pham. Thank you.
Thank you, Sam.
You're welcome.
Okay, so before start for the lab one today, I'd like to know any question to me. Okay, if it's not any question, today we start with the lab one for semiconductor. And the one we'll be doing is the full wave rectifier. Let's see. I need to turn on my camera. Did you guys see the circuit?
Yes.
Okay, today we'll be talking about the Fulwaverectifier rectification. You can see that is a Fulwave rectifier. You understand rectification, that means the converting AC signal to the pulse DC. Okay, so that's just telling you the input okay, positive and the negative. So the output, they rectify positive and also they rectify negative. So that's why they call a full wave. Okay, now, the first thing when you're looking into the circuitry, and you have to know what that name of the circuit, okay? And you understand that the name will be bridge rectifier, okay? And basically you get 4 diodes. Okay, so I go through that one, okay? We don't care on that thing. You guys have to read it. Okay, now. Okay, now 14. Locate full-wave rectification with a power supply. That is the one here. Okay. And they want to connect the circuit. This is your circuitry they want. And now in the circuitry board, you have to using the 2-pole connector to connect exactly what they wanted. So basically, from this point, they want to connect to R1. Okay, so that's why you need that 2-pole here to connect. So whenever you not follow it or understand, then just let me know. Otherwise, I keep moving. Okay, in here, they get the question here. Resistor R1 is the what? ALB. You have to tell me, ALB.
B.
B, that is correct. Okay. That's a load resistor. Okay, now they're telling you connect scope channel 1 and 2. Okay. And whatever they said, I don't care here. We're using digital scope. Set the script time or whatever. We don't care. That's it. Try to see what next. Connect the scope channel 1 probe to the top generator terminal, and it route clip to the bottom generator. Okay, so now I make the connection. Okay, so basically that is the output of the generator. Okay, will be connected to here. And the route of generator. So this is the route, okay, of generator. Will be connected to the route. Okay, then I connect channel 2 to the top terminal of the T1 secondary. Okay, so we be connected right here. Okay, my circuitry connection, something still not right. Who knows?
Gotta hook the ground.
Yeah,
Probably a
I'm not
T.
talking about connection for scope or generator. I'm talking about the circuitry,
Jumper,
still not quite right.
jumper.
You can see the circuitry here, right? Now at this one right here, that's circuitry. Do it right or wrong, or need something else?
You didn't hook the jumper to the bridge rectifier.
Okay, we need to connect the jumper for the output, right? Is it right here?
Yes.
Okay. So they can connect up the secondary to the circuitry. And now they say connect the scope channel 2. And we connect the channel 1 into the generator output. Okay. So this is the channel 1. Now I can connect channel 1. And ground will be tied to the route.
Mr. Pham, can I ask you a question?
Go ahead.
Maybe to clear this whole thing up, can you stop for a minute and go to the schematic and draw on the schematic, maybe with a highlighter pencil, where ground is and where the hot lead of both channel 1 and channel 2 is with respect to the yellow boxes?
Okay, so now, first thing you need, we have to make sure the circuitry correct right. So if you're looking on this circuitry here, okay, so that's a secondary, and this is generator, primary.
Right.
So first thing we have to connect the right circuit exactly on this one. So the first thing we have to get the jumper.
Why don't we draw ground? Where's ground at?
What do you mean the route?
Where is ground?
Oh, in the circuit.
Yeah, just use your highlighter pencil and draw ground so everybody can see ground.
Okay, let's see. You want to see route of the circuitry. This is the one at the generator right here. That is the route.
Okay. So I'm saying on your schematic on the other one, if you could just, well, go ahead, do what you want to do.
Okay, so basically, generator to get a high and a low side. The low side, that will be the route. Okay. And now they say connect the oscilloscope channel 1 out at output of generator. So channel 1 will be connect output of the generator right here. And the route has to be tied to the route of generator. Okay. And let's see, that scope channel 1 and the route must be tied to the route of generator. So let me get a long wire. To try to separate it, okay? More easier. This is the route, okay? And first I connect route of the generator and the ground with the scope channel 1. Okay, so that will be connect for generator. And now they say connect scope channel 2 to the top terminal. That means at this point right here. Okay, so basically that will be on the top terminal right here. Okay, so you can see I connect this one to channel 2. Channel 2. And the route, where they connect to the route of channel 2?
To the bottom of the secondary transformer.
Yeah,
And then you're gonna have to put a jumper from B2.
exactly.
But
And route clip to the bottom. Okay, so now I need another one, jumper. Connect to the bottom here. Okay, and connect to the scope probe channel 2. Now, okay, so basically that completely done for on of the connection. Okay, if you get a question, just bring it up, okay? And we try to see if we can get through it. Okay, adjust generator for 20 volt, which you pick 100 hertz sideways at the T1 secondary coil, which is shown on scope channel 2. Okay, so now on the scope, okay, let me go to the scope. So you can see the signal on both channels, right? Channel 1 and channel 2. the way I'm doing, I set first window, channel 1 for measure peak to peak. Second one, channel 1 for frequency. And channel 2, the window set to measure peak to peak and channel 2 for frequency. Okay. And now what they said, day 1. Okay. The way at the T1 secondary coil, they will be 20 volt peak to peak. And if you're looking right now, they say peak to peak is 32 volt. Okay, so channel 2, sorry, channel 2 will be 7 volt. They want 20. So now I want to set the channel 2 to scope probe by 10. Okay, and you know how to do. First thing, you have to go into set the scope probe for your channel 2. Okay, so I think you press the channel 2 and probe right now is 1/8. Okay, you already show. They'll show you right here. 1/8. Okay, and you 1/10. So now you can press it to make sure they get by 10 right now. Okay, and the scope probe will be set also by 10. So this one, I believe they will be by 10. Okay, so now auto set measure. So right now, what the voltage still be the same. Okay, so I make sure that scope probe, they will by 10. And they want generator 20 volt. So increase until you get 20 volt. Okay, auto set measure to see what we get. Okay, right now 27 going down. 22. Okay, 20 volt. Auto set measure, maybe make sure we get that. Okay. Yeah, around 20. And the frequency, they want, what the frequency they wanted?
100 hertz.
100?
Yeah,
100
just
hertz.
turn it one click to the left.
Yeah. So right now, the range will be 1K. Okay. So you can change it either one, 100 hertz, then generator. Okay. And auto set measure to see they can display. Okay, what frequency right now? 107. Okay, that be fine. You can go in little down. Okay, so that's what we need to set it up. So you get any question on set it up here? Make sure you understand we're using the digital scope. We're not following any instruction from the left volt. Only thing is, we want to know what the voltage they want and what the frequency you want it. And you can adjust the generator until on the scope, they're telling you that's what really they want. That's okay. Okay, any question how to set it up? Okay, if it's not, let's see what next. Okay, compare the transformer secondary peak-to-peak voltage on channel 2. Okay, primary voltage on channel 1. Okay, so basically they compare between the output of generator and the output of the secondary. Observe that the transformer primary and secondary are in phase. You understand the in phase, right? If you're moving up channel 2, you can see they will be same thing. That's the same phase. Okay, one going up, the other also going up. And if they're going down, second also going down. That should be in phase. Third, the transformer primary, secondary had a step down or step up. Which one?
It's a step up.
If you're looking on the oscilloscope, what on channel 1?
The
Channel
input voltage.
15 volt. Channel 2, 20 volt. That means input applied primary is 15 and the secondary voltage 20. So they will be step up. Okay, now observe the output across R1 by connecting channel 1, channel 2 probe to the positive. Okay. Output that point of the bridge rectifier circuit. Connect the probe round clip to the negative. Okay, so basically what they want to do, that means telling you connect into here. Okay, let's see. I move this connection into the positive right here. And the negative of the scope probe into that one. Okay, so if you're looking into the circuit, Okay, so you see I connect channel 2 here. And the round of the scope channel 2 here. Okay. And they say both alternation of the AC input waveform being rectified to DC function.
Yes. A.
Let's say I try to refer. How come my channel 2 be off? I don't need to turn it off.
You got it. You have to hook up the jumper on B at the bottom of the secondary transistor.
But for circuitry, you say connect what?
It doesn't. It looks like you need another jumper down at B.
Okay, if you say that we connect this jumper here to connect R1. Okay. That's a circuitry. I think that is connected right. Okay.
It's like you got open circuit though. Look down by B at the bottom at the secondary transistor
Second,
or secondary transformer.
second dairy transformer. Okay. You say have to connect it one, right?
Correct.
Okay. The thing is now we using the other one. Okay. That's what you said we have to connect it one. Okay. Okay. So thank you. Now, you have to say are both alternation AC input waveform being rectified to the DC portion. At the output, the answer will be what the answer is supposed to be.
Technically should be yes. A.
Hey. Okay, now, if you're looking at, okay, the output on the waveform. You can see two output at a waveform, right?
Yes.
So basically, the output here, okay, that is rectified point DC for positive, and that will be a positive for a negative cycle. Okay, so basically the answer will be Z in here. Okay, measure the frequency of the DC output wave pulsation across R1 load of channel 2. Okay, so what do you think what the frequency is supposed to be?
Should be double, 200.
Exactly. If you're looking on the oscilloscope channel 2, okay, frequency supposed to get 200. Okay, so that will be 200. And now set channel 2 vertical. Now I don't care that one. What they want, measure the pulse DC, measure the peak DC output voltage. You want to measure the peak voltage here. Okay. So what do you think the peak voltage is supposed to be?
Roughly 10.
Okay, right here, the voltage is 8.6 volt, peak to peak. Okay, that you can get 8.6
Mr.
volt.
Pham, can you use the cursor to measure?
The cursor,
Yeah,
can you see the cursor right now?
if you move it, maybe I can.
Right now I move cursor on the computer. Can you see it? Maybe not, right?
No,
I
Okay,
can see it, red dot.
I have to using the pencil.
okay,
There to the pencil right here. You see that channel 2, peak to peak. Okay. And that channel 2, frequency. Okay, I understand. That means we cannot using the cursor of the computer. So you are able to get the voltage peak to peak.
It's 8.6. It should be 10 minus. You have to go through 2 diodes. So you lose 2 forward voltages. So if it's 0.7 each, 10 minus 1.4 is 8.6. So
They want to measure the peak DC output voltage. Okay. You understand the output voltage. This is the output in here. However, in here they can get a DC voltage also. DC will be what the voltage for DC. You know what the voltage for DC? Okay, now, if you're looking on your computer, you see my moving here, right? Can you see that?
Yes.
Okay, now on that, for positive input, which diode will be on? For positive part of the signal, that will be on. If you can say together, D1, D1, then D2, D3, D4. So that will be on and that one will be on. So H1 get a 0.6 to 0.7 DC voltage when they on. Okay, so if you get a 0.6 volt here, 0.6 volt here, that's telling you the DC output will be how many volt?
So if you're using 0.6, then it's 0.6 plus
That
0.6.
normally for this lab they're using 0.6.
Okay, so that's 1.2
Right.
for the
That
two
will be
diodes.
1.2. Okay. So basically, let's see. So the answer will be
Well, the answer should be 8.6 because that's what's being measured. It shows the peak at 8.6.
that show on your display for channel 2.
Correct. And the reason why it's 8.6 is because it should be half. You rectified it, but you've lost, going through two diodes, you've lost 1.4 volts.
Yeah, that one the guy can do it. Then they take one average or whatever. They're using 0.6 for two diode. Okay, time with the peak to peak, whatever. Okay, now that's what they want set the meter. Okay, to measure what measure right here, measure the circuit average DC output voltage across R1. The meter common connect to negative. So you just using the meter connect high side here and low side here, okay, and try to get the DC voltage, okay. I don't know what they get. But there's an easy step you can do, okay? Okay, this one we don't care. Okay. Now, observe the signal across the tube. That means now they connect to the channel 2 to the output of the tree. If you're looking into your schematic circuitry, that will be the tree. Okay, so if you're looking into the circuitry, then they will be D3. And now I move the scope probe to the D3. Let's see. Okay, so I move scope probe into here. Okay, so you can see the output. They will be, that what the name for that output,
Halfway,
halfway rectifier. The thing is they connected output of the D3. Okay, so that's just a halfway. Okay,
and since it's halfway, the frequency is the same, right?
yeah. Yeah, the same with the input.
Right.
Okay, now they said set your channel 2 coupling to DC. Okay, so you can set your channel 2 coupling to AC. Channel 2 here. Right now, coupling DC. I change to DC. Okay. Let's see. Okay. And the signal will be look like. So exactly you can see that.
So,
Okay.
okay, now do auto set measure.
Okay. You can say, I forget to auto set measure. I can press auto set measure. Okay. Make it bigger. The thing is, I'm not getting anything in the generator. So you don't have to press auto set measure. They still follow it. Okay. So scope right now look like. Okay, when diode D2 is conducting, it voltage drop. So by the channel 2 waveform is the same at A or B, negative portion of the waveform, positive portion. Okay, this is right here. That's a DC. Okay, so A or B.
So you mean like A?
A, correct. That will be a minus 0.6. That means minus 0.6 volt for 1. Okay, observe on the scope screen, measure the voltage drop across D2 when it's conducting. Measure the VD2 from the round reference. So what the answer you're supposed to get?
You mean like 0 or something?
Right here.
Oh, that's like 0.6 or 0.7.
Yeah, I want to know exactly what the value.
Well, it's not 0. It's between 0 and 0.6 or 0.7, right?
Yeah. For now, for this circuitry, there is a diode, but voltage 0.6.
Okay, then it's 0.6.
It's supposed to be minor,
Oh, minus, because it's negative side.
right? Okay. They said during the negative, that means negative right here, portion of the channel 2 waveform, then D2 reverse bias or forward bias.
Reverse.
If they reverse, you cannot 0.
Oh, that's right. You get a negative 0.6.
Yeah,
So
minus
for-
0.6, then
So it's forward bias.
forward bias.
Because even though we got a voltage, correct?
Right. D2 a forward bias during weak alternation of the AC input waveform on the channel 1.
Negative.
Negative. That means answer will be A, right?
Mm-hmm.
Okay, now basically what are the diodes in the circuit? Okay, forward bias during negative. So this one is forward bias during
2
negative.
and 4, the one directly above it.
Yeah, that will be D4.
Yeah, right
Okay.
there.
Make
Right
sure
there.
you understand. For this bridge rectifier, then positive input, D1 on, D3 on. For the negative input, and the D2 on and D4 on. Okay,
Yeah, because with a bridge rectifier, you have to have 2 diodes working together.
right. Okay, the positive voltage portion of the scope on channel 2 waveform is across. What is it here? Diode D1 and load R1. Load resistance R1. And diode D4. Which one? Remember, positive voltage, that means the positive voltage D1 and D3 will be on. Okay, and when they measure, they say measure from here to here.
I think the answer is A.
Exactly. Diode D1 and load resistor. Okay. During positive portion of input waveform, D1 will be, that's a very simple question. LB.
It's B.
B, right?
Forward bias.
Okay. What are the diodes in the circuit is forward bias during positive?
It's B. D3.
B,
B.
D3, correct? That means when you answer right away, that question means you understand how the current flowing. Okay,
Yeah, 1 and 3 go together and 2 and 4 go together.
right. 1 and 3 for positive alternation,
Mhm.
and 2 and 4 for negative. Okay, so that one they can try to look in same thing. I don't have to go through that. You guys do it. That is, they want to explain more thing for you. Okay, we don't do anything here. On of that question, you just select which one. Okay, now they're talking about capacitor. Okay, you can read that. Basically, capacitor will be stored the voltage. Okay, now they want to make the connection. That's what looks like we already did it. Connect channel 1. Scope probe to the top. Output generator. We already done. Okay, that one. Connect channel 2. Probe top terminal of the secondary. Okay. That's what also we already did it. Set the sideway 60 Hz. Okay, so now they want 20 volt and 60 Hz. Okay, right now, generator they want 20. Let's see. Set the sideways generator 60 Hz. Y options channel 1 on scope adjust generator amplitude for 20 volt signal at the primary. That's what we already did it. Only thing I changing here, instead 100 Hz before, now they want 60 Hz.
They changed it to the primary coil as well. You need to put 20 volts in at the generator.
Okay, let's see. That is generator channel 1. They want it to be 20. Okay, let's see. Auto set measure. Okay, 20.6. That'd be 5. Let's see, go a little down. Okay, 20. And the frequency now 60 hertz. I have to add that generator. Okay, low to the 60 hertz. Okay, let's see what they want me to do. Connect channel 2 probe to the output terminal of bridge rectifier. Connect the ground clip to the negative. So basically, if you're looking on this circuitry, they not connect to the resistor, right? You can see that in the resistor right here. They're not connected. So we have to remove that one. Okay. And the channel 2 now will be connected to the top. That channel 2. Connect to the top. Okay. Let's see what else. Connect channel 2 probe to the positive output terminal of the bridge rectifier. Connect the ground clip to the negative. Okay, so look like now we don't connect the R1 right here. Remove that R1. Okay, then connect the scope probe channel 2 to the top, and ground will be on the bottom here. Okay, so see what they said here. The signal that you observe on channel 2 of scope a phone wave DC filter full wave or unfiltered full wave. Which one? if you're looking into the scope we on show you, they have to be full way, not the halfway. So the answer will be A or B or C. Which one you think?
I'm gonna take a wild guess. Unfiltered full wave DC.
A or B or C?
Take a wild guess. C.
You said it a C. What I mean?
Unfiltered full wave DC pulse.
Unfiltered. That's correct.
Hey, can you explain that, Mr. Pham? Why it's
And
C?
the thing is, they don't have a connector or anything, okay, in here.
Right.
So that's what they just unfiltered. When you see they connect the capacitor,
Right. You need a capacitor to do a filter, correct?
exactly.
So since there's no capacitor, it's unfiltered.
Yeah.
Okay.
And on scope channel 2, they want measure the peak output voltage of the point DC. Okay, you already see this signal output, and you can measure it. At C1, okay, across the bridge circuit output, SO, using 2 ports. Okay. Now they go to adding the C1.
Now it's filtered.
Right, exactly. So let's see, R1, and now you go to C1. Add C1. So let's see, let's go into here. You need the port to connect the C1. Then what they said. Keep the oscilloscope channel to probe, connect across positive. That's what we still do it, and negative. When you adding C1 across the full wave bridge rectifier, the capacitor form halfway diode rectifier, capacitor input filter, at the bridge rectifier, full wave rectifier with the load resistor, A or B or C. The thing is when you do the lab, you enter A wrong, you enter B or C, you get the correct. However, what I like to do, make sure you understand why you pick A or pick B or pick C. So A or B or C.
What would happen if you change the coupler? Then what would the signal look like?
Okay, you run into the circuit. Let's see. Okay, so you see that when I connect the jumper here, you connect the C1. Okay. And what the answer for ABC?
B.
Which one?
B.
I'll guess B.
Exactly. Capacitor input filter at the bridge rectifier output. This is a bridge rectifier. Okay, you connect the capacitor, that will be filter.
That's because the capacitor is blocking the DC, correct?
Right.
So if you changed on the oscilloscope your coupling, if you don't set up the oscilloscope correctly,
You get a wrong answer.
right, would you show that signal difference on the oscilloscope, the difference of how the signal will look when you have your coupling set from DC to AC so that we can see the difference and why it's important for the oscilloscope to be set up correctly?
Yeah.
Thank you.
Okay, so look like if you're looking at the oscilloscope, between channel 1 and channel 2. Okay, channel 2 right now, we're using DC coupling. I can to AC coupling. You can see the signal. Okay, channel 2. Okay, so just go to the capacitor. Go fix it channel 2 off on the time.
Did you want AC or DC coupling?
AC coupling.
The channels have just changed their placement for the display. Well, what happened when the coupling changed is the channel 2 drop. Looks like it drops more negative.
Let's see. It's just a DC coupling. See what happened. Okay,
Yeah, that question says the signal on channel 2 is a constant DC voltage because the whatever. The capacitor charge up to peak output.
Yeah.
voltage.
let's see. The signal on channel 2, a constant DC voltage because circuit no longer full wave rectified when C1 is connected at the output. Capacitor jack up to the peak output voltage and stay at that value because there is no load resistance to the discharge. Okay, so which one do you think?
I think B.
B is correct. The thing is, you get the signal input, so they jack the capacitor up, okay? And do not connect to any load, so they cannot be discharged, okay? That will be B. Now, with the meter, measure the DC output voltage across the bridge rectifier. That means now you take the meter and you measure DC voltage, okay? I'm not trying to do it in here. And with the C1 connected, your measure DC output voltage around 20.5 volt DC, equal to the peak output voltage, okay, 13 volt without C1 connect, okay? So without the C1 connect, if I'm not connected C1, let's see what the voltage here. Around 12.6 volt, okay? So when I connect the C1, okay? So,
The difference in 12.5 and 13 is 0.7.
right. Okay, so that's really okay.
So what was that? What was the answer to that one, Mr. Pham?
Around 12 point something.
No. I'm saying the answer, was it yes or no?
Yeah, let's see. Without C1 connect,
That's with C1.
yeah. If you not connect capacitor here, okay, then the voltage, they say output voltage 12.5, essentially equal to the peak voltage 13 volt without C1 connect.
So would that be yes or?
I think that should be it.
C1
12.5 and 0.7 would be 13.
That's the thing that you get a DC voltage.
What you think, Lowell?
DC is being blocked.
That's the output here, okay? So basically, the capacitor here, they get only AC, okay? So if you want the answer, I can tell you.
If C1 is not connected, then technically you're not blocking any DC.
Right. When you connect the C1, they will be jack it up.
So if it's essentially, if you're going only with essentially 12.5 is 13 volts, so it'd have to be yes.
Yeah, that's what I think too. Okay, we
Okay.
got it, Mr. Pham, we got it.
Yeah. Set them onto scope with the lower vertical, whatever here, I don't care. Either ripple content of the C1 voltage signal. You can see any ripple or not.
So I guess they're saying, is the ripple content of C1 voltage insignificant? I guess the answer would be yes.
No,
I mean, ripple, still, right, it's no, it would not be significant.
the thing is, they have to get a discharge.
Right,
And now no loading. So they cannot discharge.
but the ripple content is insignificant. So the answer is no, correct?
Right.
All right,
Now remove C1 and connect R1 as so. Okay, so basically now they connect it back to R1.
hey, Mr. Pham, if
Yeah.
in this case right here, where they said, I know they said disconnect C1, but if you had C1 and then and the load connected in parallel, what would happen?
If you connect R1 and C1, right?
Correct, in parallel on the load, what would happen?
Parallel. Okay, let us looking into the circuit. So now if I connect R1, okay, and look like you can connect R1 and you cannot connect to C1.
Oh, you can't?
Yeah, on the circuit,
All right,
okay?
thank you.
So let's see what next here. And the output on channel 2, unfiltered output of diode full wave across 47 KO. Filter output of a diode full wave. So if you're looking into that one, the answer will be which one? Quickly.
It doesn't have a capacitor, so it's unfiltered. Is that A?
Right. Unless you when they connect capacitor, they can
Right.
get a filter. And now connect C1 and load resistor R2.
Yeah, that's what I think I just said a little while ago.
Okay,
Mhm.
so I quickly connect load resistance and R2. So now you need to connect okay, that means connect to okay, resistor and R2. The thing is, next time I have to figure out how I connect display board.
Hey, Mr. Pham,
Yeah.
and this is the one where I was asking about the capacitor and the resistor both being on the output, because you early on you said you need a resistor on the output, like if the capacitor charged up and for it to discharge, you need a load resistor, right?
Right.
So when you got the capacitor and the resistor both there, what happens?
That means they charge it up to the resistor. Okay?
The
To
capacitor charges
capacitor,
up.
sorry. To capacitor and they will be discharged to the resistor.
Okay, so the capacitor charges up, and then when it gets fully charged, then the resistor is used to discharge.
When they try to charging up, and also when you get a load, they will be discharged.
Okay.
what they try to show you here, they try to see the ripple. Okay, so now basically they connect to C1 and also connect to R2. Okay, so you can see right here, connection here connect to the C1. And also they going to connect to R2 right here. Okay. And what else they want? Filter output of a diode full wave across them. That answer will be B. Okay. Adjust scope channel 2 to observe if there is any ripple to the DC output. Is there any ripple across rectifier? Okay. So now, let's see, on the output rectifier, okay? Let's see. Okay, so you can see on the scope, channel 2. Now they get that's what we call a ripple. Okay, if we try to make the voltage changing, see that? That's what they call a ripple. That means on the top of the DC, they can get the signal, and that signal will be a ripple. Basically, ripple is just the noise, okay, on the DC.
Approximately how big or small is the ripple? Approximately.
Now, that normally when we design the circuit for the defense system, they're asking you output they want it 1 millivolt ripple maximum. The thing is on the DC, they want a straight line. They don't want any on the top. That means a ripple on the top of the DC voltage.
So 1 millivolt is considered with small or large ripple.
That is normally okay. However, depending on what they asking for.
Okay.
Okay, if they want 0.1 millivolt peak to peak, that means you have to design the ripple like this one coming out.
Is that
0.1.
is that ripple adding a stability to the frequency? What's the primary purpose for the ripple?
Now they have to design to understand it when the capacitor charging and discharging depend on the time constant. We already know tau equal R times C. Okay, so you want the time for charging is much longer than the time for discharging. That means they charge full it and they will discharge very short. So that's why they can make a constant DC voltage.
Faster the charge or faster the discharge, right? That's what you want.
You want a longer time for the charging, but you want a very short time for discharge.
But you want a fast fill, but then you want a fast discharge, but then a fast fill, right?
Right. At the output, you want it to be a flat. I don't want ripple. So when they discharge very short, okay, then they already keep in charge again. So that will be make that to be a constant, and the ripple will be smaller. Okay. Otherwise, the ripple you're looking now on the oscilloscope, that is they want to show you how the ripple will be look like. And basically that on the top of the DC, like you get 5 voltage DC, 10 voltage or 12 voltage. If on the top they get a ripple bigger, that got a problem for the circuitry. They're not working right. So they want that to be a flat. Okay, so they want to calculate the ripple peak to peak, then they can measure, okay, peak to peak of the ripple. Okay, so now I can stop in here this time. Okay, next time we'll keep going.
That it for the day, Mr. Pham?
Yeah. So, you get any question? Otherwise, okay, will be good night.
Good night.
No, it's front.
Good night.
Good night.